Yesterday we talked, and I want to continue today with multi-group fairness. And kind of pick off where we left off in multi-group fairness. We're requiring that some property holds. So for every set in a rich collection, C, probably, possibly an exponential size collection. And we talked about multi-accuracy, where we are requiring that for every one of these sets simultaneously, the expected predictions are close to the expectation of the outcome. So the expected prediction is close to the fraction of people in that set who get a 1 outcome. That's multi-accuracy. And we'll talk today a little bit about multi-calibration, which I mentioned but didn't really define. So here we are requiring calibration for every set in the collection. Namely, for each and every one of these sets simultaneously, looking at the individuals in that set. For each prediction category, so suppose the predictions are discretized and we have the people for whom the prediction is 0 and 0.1, 0.2, maybe we have a finer discretization. But for every prediction category, think of these as deciles, within each set, the fraction of people who get a positive outcome is roughly what it should be. So within the set S of the people within that set who had prediction 0.2, about 20% should have a 1 outcome. Is that clear? So I just want to tell you in a word something about defining these notions, in particular calibration. So there are different ways of defining. Perfect calibration is easy to define. We just defined it. In words, approximate calibration, you have to be a little bit more careful. So for perfect calibration, I would say that for every prediction category V, so now we are going to look at the people for whom the predictor predicted the value V. So that's going to be the set S sub V. So those are the members of S for whom the predictor P tilde predicted V. And now what we want is that for every set S in C and for every V, that's perfect multi-calibration, the expectation of the Y outcomes for people in that set, so the expectation of Y conditioned on landing in this, on being in the set S and having prediction V, this should be exactly, if we're talking about perfect calibration, this should be exactly equal to V. Any questions? Totally clear? Good. Let's aim for totally clear. It should be. And then if I want approximate calibration, so the first thing, which is pretty easy to do, is that I would say that I want the expectation to be equal to V up to plus or minus alpha. Okay, I want to allow an alpha additive error within that prediction category V. So any problems with this? So it's still a little bit problematic, even though we're talking about sets that have sufficient weight at least tau, according to the underlying distribution. So the set S is large enough. It has enough mass for us to sort of have these kinds of approximate guarantees. Now when we're talking about the people within S who got prediction V, maybe that's just one person. Right? Like maybe we don't have sufficient mass within the prediction category V, and then it'll be hard to get this notion of approximate calibration. We can't get the, it's not a meaningful guarantee, certainly if we're just allowing an alpha additive slack, if the category is too small. So there are various ways of handling this. One way of handling this is we just say the predictions are discretized, so there aren't too many categories, And we insist on approximate calibration holding for every category that is large enough, that has at least tau people in it. And the other way of doing it is we just allow an alpha fraction of S to be sort of dropped out. So we don't insist on any calibration guarantee for them. So we'll call the remaining members of S S prime. So there's an alpha mass for which we don't have to be accurate, and then we'll take the expectation just on the remaining people in S. So if a category is too small, we can just sort of drop it out completely. Okay? So then, yeah, if you're conditioning on an empty set, things are not well defined. But what I mean here is that if there's no one left in this category, if the category is too small, we'll just put all of them away. There won't be any of them in S prime, and then we'll have an empty condition here. Okay, so that's just meant to make approximate calibration feasible given a sample. Right? We don't want to use properties that are sort of too delicate and, to the presence or absence of single individuals, or where we can't really get good approximation guarantees from a small sample. And that's how we define it. Yeah, if you lost me along the way, it's not super important. Just know that we can define approximate calibration, and it can be a little bit subtle. Good, so multi-calibration, we require this notion of alpha approximate calibration for every set in the collection. And then in terms of achieving it, an algorithm that is very similar to what we saw yesterday for multi-accuracy will work. We start with a predictor, either one that's given to us or just by giving everyone prediction 0.5, and we start iterating. Okay, we start looking, does there exist a set within which there is a category V of predictions where the expectations are not what they should be. Okay, and if we find such a category within a set, a large enough category within a set, we update those people in the set S who got prediction V. We add delta to their predictions. They go from V to V plus delta, and we go and we iterate. And a similar kind of potential drop argument would say that the number of iterations is bounded. Yeah, let me say one thing. I'm kind of talking in the air a little bit, but I do want to say it. So when we were talking about multi-accuracy, all we cared about was for the algorithm. Remember, we stopped and we said, where is this algorithm using the data? And the multi-accuracy algorithm was just using the data in order to estimate all the expectations of the outcomes on all the sets S. And that's why we needed the data. We just needed this collection of size of C expectations, and we were done. For multi-calibration, it's a little more subtle. So does anyone see the subtlety? Is there kind of like a fixed collection of expectations that would suffice for this multi-calibration algorithm that I described?
Well, there's no guarantee there will even be ever a sample X that has the value V under V tilde, right? So.
Right, but somehow, if there's no sample that has V, I don't care about categories that are too small. So the question is there a set and a category that are large enough where the expectation is off, and then I can correct and iterate. If not, then we've already achieved approximate calibration.
No, but what I mean is that somehow in order to average over, in order to get an empirical average for an estimate of that expectation in SV, you need to have some people who live in SV, right?
Yes.
Will pop up from your sample.
Yes.
There's no guarantee that they will be there.
There's no guarantee they will be there, but somehow you would hope that the sample accurately reflects if there are people in the underlying distribution where they get prediction V, they should appear in the sample, and you'll be able to estimate. But I think you're on the right track. There's a subtle, does someone else want to?
You need the power set of X to check all the sets, every possibility.
So yeah, the power set of X is too large. I can't get accurate expectations for all of them. But notice that there's something circular about, go ahead.
The sets depend on our estimation.
Exactly, the sets depend on our estimation. So the set that I'm looking for, now I have my fixed set S, but within S, the people who got prediction V, that's not static. That's changing as the predictor is changing. So I don't have a static, fixed in advance collection of sets where the expectations are sufficient for me. But I need to keep estimating these expectations, the expectation of Y, over the people in S who got prediction V. Those keep changing every time we update the predictor. Okay, so in fact, sample complexity, maybe you need to draw a fresh sample. We have something adaptive here. We can't just use the same samples we used before. So either we draw a new sample every time, or we need some more sophisticated analysis. And as far as I know, I hope I'm not getting this wrong, the question about whether the sample complexity of multi-calibration, can it be as small as the sample complexity needed for multi-accuracy? I believe that's open. At the moment, we have a gap. And I don't think there's a lower bound. Cynthia, is there? Do you know of a lower bound? Yeah. So that's a good question, I think, to think about. There's some work on that by Mansour, Cohen, and someone whose name I'm unfortunately forgetting. Okay. So we will speak a little more about multi-calibration throughout the day today. I wanted to say again, calibration on its own, we said, is stronger than just requiring accuracy of the expectation. It implies accuracy of the expectation, but it's stronger. Still, on its own, calibration just for a global set S is not a super strong guarantee. Like if we were just requiring it for one set, that would still allow us to smush everyone together. Right? Remember, if half the people are ones and half the people are zeros, we can smush everyone together and give them probability a half. And that'll still be a calibrated predictor, even though we're not making meaningful distinctions. So here, too, the power of multi-calibration is coming from the fact that we have a very rich collection of sets, and we're requiring calibration for all of them simultaneously. Okay, so...
Instead of, for example, asking for many sets, you could ask for higher moments, or having the same...
So the problem with... Yeah, so great. So having, the same moments or entropy as what is the problem?
As a complement of the set or something. I don't know.
Yeah, exactly. So I don't know, maybe the reality is that everyone in this set is a half, and maybe the reality is that there is some way of separating them. But just by looking at things in the set overall, I can't tell these things apart. So there isn't like a fixed benchmark that I can compare with and sort of require that the predictions are making, at least, I don't know, some meaningful distinctions above some threshold, because maybe that's impossible. So I don't know sort of what the ideal is. That's P star, it's out of reach. So I don't think that just looking at the global set and looking at more statistics is going to help us. We do need to look inside the set and try to see whether we can identify subsets where we're making meaningful distinctions. Okay, so I want to talk today about the auditing problem. Okay, so by that all I mean is given a predictor P tilde, checking can we determine whether it is multi-calibrated or whether it is multi-accurate? So is a given predictor P tilde C alpha tau say, let's stick to multi-accuracy for now. Okay, so auditing always is a really important, there's two central algorithmic problems, once we have a notion of fairness or any notion that we want predictors to achieve, we want to know how to learn such a predictor. We talked about that yesterday. And it's also really important, given a predictor, is it possible to determine whether it does or doesn't have the property that we're after? Okay. So we have the auditing problem, we have the learning problem, and in fact, the algorithm we saw yesterday shows a reduction from the learning problem to the auditing problem, right? In order to learn, all I need is to be able to look at my current predictor P tilde, try to identify whether there is a set where its expectation is not accurate, And if so, I update and I go again. So if I can solve the auditing problem, I can also learn for multi-accuracy. It's not a general statement, but for multi-accuracy and multi-calibration, it's true. And in particular, what we said yesterday and what we'll say again today is that information theoretically in terms of sample complexity, how many samples do we need in order to audit? So we need some access to the underlying distribution to know whether the predictor is multi-accurate. How many samples do we need altogether? Okay. Log size of C divided, I think it was alpha squared tau, but let's not be too finicky about that. It's a polynomial that depends on 1 over alpha and 1 over tau. Samples were sufficient. So we can audit using a few samples. That was also why we could learn using a relatively small number of samples. But what about computation? So computationally, the way our algorithm worked was we just had to go, sort of brute force over every set in the collection C, and for each one of them check whether the expectation given by the predictor is close to the actual fraction of ones that we're seeing on that set in the data. Okay, so that was very computationally intensive if the set C is exponential. And what I want to say is that this problem is a central problem. So we can solve it by brute force, but that's very expensive. And sometimes you can get away from this, sometimes you can't. There is a very close connection or an equivalence, I should say a loose equivalence, to agnostic learning. And I'll say in a minute what that is, what the agnostic learning task that I'm talking about is. But the takeaway from this is that theoretically speaking, at least, we said it on the first day, agnostic learning, agnostic pack learning is computationally hard in the worst case. So we know how to build data distributions such that even for simple hypothesis classes or collection of sets, the problem is computationally hard. On the flip side, we do have interesting algorithms, and in practice, the problem is often easy. And that may turn out to be the case for the auditing problem as well. There may be, theoretically, we're going to see a hardness result in a minute, but in practice, maybe heuristic algorithms can solve it pretty well. Okay, so questions about that? Yep.
So is it the case that heuristic, is it that we're not often in the worst case, and that's why heuristic algorithms work? Or is it that we don't know as yet how to analyze heuristic algorithms and explain why they work?
I think all of the above. So no, the second is certainly true. So this is, I think, another defining problem of machine learning. Why do the heuristics work when the theory says that the problems should be hard? And probably the explanation is that the instances, the actual data distributions we're talking about, are not the hard ones. The ones we see in practice are not the hard ones, from the theoretical hardness results. But sort of explaining, sort of characterizing when these algorithms run well, when they don't, developing an understanding of this, I think, is an excellent question. Okay, so what do I want to say? I want to show a hardness result. I want to say that auditing, whether a predictor is multi-accurate or not, is not going to be much easier than agnostic learning on a hypothesis class that's closely related to the collection of sets. Okay, so what's the agnostic learning task that I want to define? This is what's known as very weak agnostic learning. The name is deceptive because even though it's weak, it's computationally very hard to achieve this modest goal. Go ahead, I hear you.
Just wanted to most of the time your algorithm will actually be spent looking for the set S with which there's a big discrepancy.
Yes.
So most of the time you will actually have very good, on most sets it will be actually quite good, and potentially the computational complexity comes from just...
That's a concern. If it's easy to find, so long as it's easy to find a bad set, a set where you're doing poorly, maybe you're doing poorly on all the sets or something like that, then things will be easy. These loops will sort of go very quickly.
Right, because each time you chop away at
Yeah.
this potential.
Yeah. But at some point, you'll start being good on a lot of the sets, and then finding the needle in the haystack, the set where you're not good, may or might become hard.
Especially if the collection of sets doesn't have a very nice structure.
Okay, so we're going to agnostic pack learning, and what's the task we want? Again, we have a data distribution on labeled examples, and we have a hypothesis class. And we want to find out whether there is a hypothesis in this class that is even a little bit better than just random guessing on this data. Okay, that is the task of weak agnostic learning. So we have some hypothesis class H, and if there exists some hypothesis in this class whose error probability is even a little bit more than a half, a little bit better than random guessing. So we can always do random guessing, but if one can do even a little bit, even rho, that's a p that's actually a rho, a little bit better than random guessing, then we need to find, the task is to find some other h prime. Doesn't have to be the same one. We don't have to find it. We can find something else. We can find something that's not even in the class, what's known as improper learning. But we want to find something that does a little bit better than random guessing, if such a thing exists within the class. Okay? So this is much weaker than what we talked about on the first day, right? We're not trying to compete with the best hypothesis in the class. We're just saying if there's something that's even a little bit good in the class, we need to find hypothesis that also does better than random guessing. Usually, rho is larger than tau. So, if there's something that has advantage 0.51, maybe we just need to find something, that has advantage 0.501 or something like that. Okay, so it's a relaxed sounding task, but in fact, it is quite difficult computationally. There are also reductions from weak agnostic learning using boosting to strong learning. I don't want to get into those. I just wanted to find a task, and I want to tell you that it's computationally hard, and then show a reduction from agnostic learning to auditing for the same, that more or less maintains the hypothesis class is going to be more or less the same as the collection of sets C. So I'm defining a computational problem, and it is only easier if I allow you the flexibility to return some other h prime. If you can return h, great, do it. But it might be easier, and we'll see an example, to find some h prime that is not quite as good as h.
Oh, because, I see, so h is not a computable function in your class, right? So you would like to find some...
H is a computable function in my class, H, the hypothesis class, capital H. And what I want to say is that if this class can make meaningful predictions, even a little bit better than a half, then you have to find for me something that is doing better than a half. But I'm making your life easier by allowing you to return something weaker. It still has to be bounded away from a half, but maybe by less than the hypothesis H. So if I just said return H, this would be a harder task, right? Find some H that does better than a half if it exists within the class large H.
So nobody gives you H.
Nobody gives me H. I don't know what it is. So yeah, I should say if there exists some H somewhere, and I don't know what it is. Okay. So let's see this reduction. So what's the reduction? What does it need to do? What are the semantics? So we get as input some class large H, and we have samples from an unknown distribution D. That's sort of in the background. And we want to create from this, create a class C sub H and a predictor P tilde such that finding a multi-accuracy violation, meaning a class, a group S in this collection C sub H, where multi-accuracy is violated with respect to the underlying distribution D. So finding such a violation essentially boils down, or essentially can be used to find some H prime for the weak agnostic learning task. Yeah. So I should say, what I want is to create this predictor P tilde, and I want to say that if there is no hypothesis in H that has advantage bounded away from a half, has error probability or success probability bounded away for a half, then the predictor P tilde will be multi-accurate. But if there is such an H, such a little h in the hypothesis class H, then P tilde will not be multi-accurate. And in fact, any set that, if you produce for me a set where there is a multi-accuracy violation, I will be able to use that to identify some hypothesis H prime that has success probability bounded away from a half. Okay? And what that means is that if agnostic learning for this collection H is hard, then auditing multi-accuracy for the collection of sets CH, which we'll see is more or less H, will also be hard. Does that make sense? Okay, so let's do it. So the predictor P tilde that we construct is going to be very simple. It's just going to predict a half on everyone. So P tilde is just going to be the constant half predictor. Okay, and the class, so we're going to audit P tilde for essentially H alpha. Let's forget about tau for right now, multi-accuracy. Let's put it in there, tau, multi-accuracy. So remember, hypotheses for the tau, these are classifiers for pack learning, so they're just functions that output 0 or 1. So in fact, they define for us, every hypothesis defines a set, the set of x's for which the hypothesis says 1. So I just want to augment this collection of sets a little bit. For every hypothesis, I want to include its set and also the complement. Okay, so for every hypothesis in H, we'll have the set on which the hypothesis says 1 and also the set on which the hypothesis says 0. And I just audit for multi-accuracy of this. And my claim is that if in the original problem, if in the agnostic learning problem, there is no hypothesis that has advantage bounded away from a half, then the predictor will be multi-accurate. Intuitively, that makes sense, right? There's no predictor, for all the predictors here, when the predictor says 1, it doesn't really have advantage, right? Like it's half the time the answer is 1 and half is 0 because the accuracy of the predictor is about a half. And when it says 0, half the time the answer is 1 and half the time the answer is 0. So our expectations are always around a half and our predictor is multi-accurate. Okay. Yep?
So you're assuming that the base rates are fairly balanced here?
I don't need to assume that the base rates are fairly balanced. So let's look, that's intuition for the reduction, but what's bothering you?
Just if you guess a half for everybody, that you would have error about a half.
Yeah, so sorry, if the base rates aren't balanced, then there's a very easy hypothesis. The constant hypothesis has success probability bounded away from a half. So for the agnostic learning problem to be hard, yes, the probability of seeing a 1 label has to be around a half. Otherwise, the task is easy. Yeah.
And does it matter if it's a deterministic or randomized classifier here? It sounds like the output you observe are the 0.
Yeah, I'm thinking about deterministic classifiers in terms of my learning task and deterministic sets in terms of multi-accuracy. Okay, so at least in terms of intuition, we already, oh no, we're okay. Started at 1/4 past. Okay, so we said if really there's no good hypothesis in H, then it makes sense that P tilde is multi-accurate. And the converse will also be true. So if there is some H that's making meaningful distinctions, some little h in the class H, then there will be some set here where predicting a half is going to be bounded away from the correct expectation. So let's do both directions of the reduction. So in one direction, I want to say that if the auditor for multi-accuracy, if the multi-accuracy auditor finds some collection S, then we can build the H prime we need for agnostic learning. And in the other direction, I'll need to show that if a good H exists, then the auditor will find a set S. Those are the two things that I need to show. Okay. So what does it mean that the auditor finds such a set S, or let's call it H? Just in line with what these sets actually are. So that means that the expectation that the expectation of y conditioned on h of x being 1, okay, on membership in the set defined by h, is bounded away from, so this is the true expectation, and it's bounded away from what we've been predicting, which is always a half. Okay, so if the auditor finds a set H, that's what it means to not be multi-accurate. And without loss of generality, let's get rid of the absolute value and assume that we're bounded away from a half from above. Yeah, we're bounded away from a half from above. So rewriting this, what we have is the probability, the expectation of y conditioned on this being in the set on h saying 1 is a little more than a half. Okay, so how should we build now a predictor or a classifier that does well on the underlying distribution? It seems like we're very close, right? When this classifier says 1, more than half the time it's right. So we're bounded away from a half the way we wanted to. So can we just use this classifier? Is it going to be good with respect to the underlying distribution? So I have an auditor, and the auditor returns for me some h. Okay, now I want to say that if it found an h where there's a multi-accuracy violation, so I got it from the auditor, then I can use that to get advantage bounded away from a half. Okay. So can I just use this h? We don't know what it does on 0, right? So maybe on 0 it's really terrible, and so it has advantage a little more than a half on the 1s, but it's terrible on the 0s. When it says 0, it's making tons of errors, and so overall its error is not so good. Okay, so no problem. We'll just define a new hypothesis, h prime. I'm sorry, I'm going to write it as probabilistic, but you could make it deterministic if you wanted to. So our h prime, if h of x says 1, it just outputs 1. And we know that more than half the time that'll be the correct answer. And if h of x is 0, what should it do? Flip a coin, exactly. So that means that exactly half of the time it's going to be right. Right? When h of x is 0, h prime is going to be right exactly half of the time. When h of x says 1, it's going to be right more, significantly more than a half of the time, and so its total success probability is going to be bounded away from a half, which is what we wanted for weak agnostic learning. Okay. Notice that here I was using the fact that I don't have to return exactly the h that I got. I can sort of mess with it to make it a little better. Yeah? Yeah, we need the complement for the other direction. Yeah, here, when I said without loss of generality, I really meant it. I don't need the complement for the other direction. If it was the other way, I would just keep h prime would do the same as h on zeros and would flip a coin on ones. Okay, so we already said if the auditor gives us some set where there's a multi-accuracy violation, then we can use that to solve the agnostic learning problem. Now I want to show that if there exists a good h for the agnostic learning problem, then the multi-accuracy auditor will find something. And then we'll be done. Okay, so in the other direction, I want to show that if there exists some h that is good, where good means has advantage more than half plus tau, then the auditor will find it, or will find something. Meaning that multi-accuracy does not hold for this predictor p tilde. Okay, so just say that, and p tilde is not multi-accurate. Okay, so suppose there exists some h, and its success probability is more than a half. More than a half plus tau, plus rho, sorry. Okay, so if its success probability is more than a half, then either its success probability is more than a half when it's saying 1, or its success probability is more than a half when it's saying 0. Right? It can't, one of the two has to be correct. So let's assume without loss of generality, here, without loss of generality is folding in the complement of the set. That the probability that h of x equals y conditioned on h of x equals 1 is bigger than a half plus rho. Okay? So notice once I've done this conditioning, I know that h of x equals 1. So really we're saying that the probability that y equals 1 conditioned on h of x saying 1 is significantly more than a half. So this h is identifying for us a set where more than a half plus, I guess rho and p are really bad to confuse. So sorry, bear with me. So this h is identifying for us a set where the fraction of ones in the labels is significantly more than a half. But what is the predictor p tilde saying? It's saying a half. Right? So this is a violation of multi-accuracy. So p tilde is not multi-accurate, in particular on the set h defined by h. Okay, and if I assumed if the without loss of generality went in the other direction, if what was happening was that the predictor was correct on zeros, then it would be the case that whenever the predictor says 0, the fraction of ones is significantly less than a half, and we would have a multi-accuracy violation on the complement of the set H. Okay, and we're done. So we've seen in one direction that multi-accuracy is no easier than auditing. Auditing for multi-accuracy is no easier than agnostic learning. And there's also a reduction in the other direction that I'm not showing today, namely that it's not harder, right? If you do have weak agnostic learning for a class, you can also do multi-accuracy and multi-accuracy auditing, and with some more fanciness, you can also do multi-calibration. Good, so I think that's what I wanted to say about the auditing problem, and I hand things over to Cynthia, and I guess I did go for the whole hour, so we take a break. No, I didn't, sorry, again, yes.
We went for 45 minutes, but I think it makes sense to break a little bit early before starting something.
I think that's great. So let's break for half an hour, and we come back at 10:30.